Welcome back. I wanted to wrap up our discussion on factoring polynomials by jumping right into our last two techniques for factoring polynomials. So in the last video, we introduced to you guys the concept of the greatest common factor when you're comparing two or more terms. We factored out the greatest common factor, and then we also looked at the factoring by grouping technique. Okay, so now we're going to learn two more techniques. The first one's going to be called factoring trinomials using the AC method, and then we're going to factor binomials, but there are a special set of binomials called the difference of squares. Okay, so let's jump right into it. Here we go. So the first thing that you have to understand when we're factoring a trinomial is what is a trinomial? Well, it's right there in the name, right? Tri means three. And so a trinomial is a polynomial that has three terms, okay? So you can't use this technique unless you're dealing with a polynomial that has three terms, okay? So the AC method is a technique that's used to change a three-term polynomial into one that has four terms. Now, the reason we're doing that is so that we can take a three-term polynomial like the one that we see right here, break it up into four terms, and then we can go back to factoring by grouping. So in reality, we're not going to be learning much of a new technique at all. We're just trying to convert something that has three terms so that we can go back to a technique that we've already been practicing. Okay. So how does that technique work? Well, first, given any polynomial, you want to look at all of the terms and count them, right? So that's going to be part of your factoring checklist. Always make sure that you're dealing with the right number of terms for that particular technique. Okay, so we have one, two, three. That tells us that we probably want to use the AC method. But we always want to go ahead and check to see if these guys have a common factor that we can take out, because that may help simplify the problem a little bit. If you spend a little bit of time looking at this polynomial, however, m squared and m, they share a variable term m, and that's about it here. We don't have a GCF because not all of these terms have that variable m, and similarly, there's not a number other than one that divides m squared, m, and negative 90. Okay. So right away, this looks like a really good candidate for factoring using that AC method. So what we're going to do to start this process is first, we want to label each of our coefficients. So what is the number that's in front of m squared? You might ask yourself. We'll label that A. Well, that's going to be equal to 1, and that's because we don't see a number in front of the m squared. In other words, we just have one m squared, so that coefficient's 1. We're going to label the next coefficient B. Okay, so what is the number in front of the m here? Well, it's a positive, but we don't see a number here. So again, we understand that that's a coefficient of 1. Okay, the last coefficient we're going to label C equals is whatever this constant is. So that's going to be negative 90, and we want to make sure that we're taking that negative sign, because if we don't, then we might run into making some mistakes. Okay. So we label our coefficients for the trinomial A, B, and C. Okay. But the reason why this is called the AC method specifically is because we need to take uh, the A here and multiply it by the C to start this process off. Okay, so we're going to hold off on figuring out what to do with that B for now. But right now we're going to say, okay, well, what is the coefficient for A? That's equal to 1. And we're going to multiply that by the coefficient C, which is in this case negative 90. Okay. We can multiply that out, and then we know that 1 times 90 is negative 90. Okay. So we're just doing a little bit of scratch work off to the side. I like to sometimes partition my piece of paper just so that my scratch work doesn't get in the way of my actual work that I'm going to be doing over here on the left-hand side. It's a really useful thing to be able to organize yourself in space just so you can think clearly about what's going on. So this is going to be a helpful space to work out some of our thoughts, but then we're going to come over here and see how we're going to break up this polynomial. Okay, so we multiplied a times c, and we got negative 90. What you want to do now is go ahead and make a factored t chart for 90, not really paying too much attention to that negative sign just yet, but we want to say to ourselves, what are all the factor pairs of 90? Okay, well, that's 1 times 90, 2 times 45, I believe. Okay, and if it starts to get a little bit dodgy right off the bat, we'll grab our calculator, as we always do with these factor t-charts, and then just start sort of dividing to see what's going to break up that 90. So we have 90 divided by 3. That's 3 times 30. 90 divided by 4. That doesn't work. 90 divided by 5. 5 times 18. 90 divided by 6. That is 6 times 15. And notice that as these numbers are getting bigger, these numbers over here on the right are getting smaller, and at some point they're going to converge, and that's how we know that we can stop. So we have 90 divided by 7, it's not going to work. 90 divided by 8, also not going to work. But then 90 divided by 9 is 10. So 9 times 10 seemed obvious, but we went ahead and went through that whole process. The next number would be 10, but we already have 10 times 9, so we can stop there. Okay. So now that we have listed all of the factor pairs here, what we're going to do is select the pair of factors that will add or subtract to equal whatever this number is in the middle, this B term. Okay. Okay. So we want to see, okay, 1 plus 90, that would be 91. Too big, right? We're trying to match this coefficient B. So we're going to go down the list. 2 plus 45 is 47. That's not going to work. 3 plus 30, that's not going to work. 5 plus 18 is not going to work. And we're trying to get 1, okay? Either by adding or subtracting. So we're just trying to see if addition works. 6 plus 15, that's not going to give us 1. 9 plus 10, that's not going to give us 1. Okay, so then we'll go back and subtract. Maybe we'll try 90 minus 1, that's too big. 45 minus 2, that's too big. And we'll go down the entire list again. 10 minus 9, that gives us 1. Okay, so I'm going to go ahead and circle the factor pair that is going to work. Because what we're really trying to do is work out two conditions. And the first condition may seem obvious, that the first factor that we choose times its factor pair, they needed to multiply to give us negative 90. But then when we either add or subtract them, so in this case we're trying to subtract, we need to get the value of that middle coefficient, which is 1 in this problem. Okay. So we said, okay, well, 9 times 10, does that give us negative 90? No, not quite. Okay, so maybe we'll hold off on thinking about that for a moment. But we know that we need to do maybe 9 minus 10. Well, that wouldn't work either, because 9 minus 10 would be negative 1. Here's the thing. You get to choose which of these numbers goes first, okay? Or which number you're subtracting from the other one, okay? So what we need for this particular problem is 10 minus 1. I'm sorry, 10 minus 9, because that would give us a positive 1, okay? So we've met that condition, okay? But if we were to switch the order of 9 times 10, would that give us a negative 90? Well, no, okay? So something funny is going on here, and this is what you really want to think about, okay? First of all, the number that we're trying to get when we multiply is a negative 90, okay? That means that when we multiply these factor pairs together, whatever those pairs happen to be in this list, that one of them has to be negative to give us a negative 90. So because this guy is negative, that means one factor must be negative. Only one factor must be negative. So we get to choose which factor is going to be negative so long as these two conditions are met. So like we said, we wanted 10 minus 9 here so that we get a positive 1, okay, because that condition needs to be met. But now here, 10 times 9 or 9 times 10, we get to choose which of these will be negative, and only one of them can be negative. Well, they have to be the same two numbers here. 9 and 10, 10 minus 9. So if this is where we put the negative, we put 10 minus 9 to get that positive 1, then that means that we needed a negative 9. Okay, so I'm going to put a negative sign on that 9. Okay, okay. If that makes sense, then we should be able to proceed. Now we can go over here and say, let's think about why we were trying to get that positive 1 to begin with. We want to take these three terms and break it up so that we have four terms. What we're going to do, and the reason why we did all this mess with the AC and all this factorization and trying to pick the candidate of numbers or the candidate of factors that will give us a 1 and a negative 90 is because we chose a negative 9 and a positive 10. Okay? Those numbers multiply to give us the negative 90, and they add or subtract to give us the positive 1, this value of b. Because what we're going to do next is take this middle term, which was originally an m, and break it up into two terms. Okay? What we're going to do is instead of writing m in this polynomial, we're going to write negative 9m plus 10m to replace this m. The reason why we can do that is because if we were to combine these like terms, negative 9m plus 10m, you would get 1m. Okay? So making this replacement doesn't really change the value of the original problem. Okay? And that's what we want. We don't want to change the problem. We want to just rewrite it with four terms. So if we replace m with these two terms, which we obtained by doing this factoring process in the AC method, all we need to do now is bring down the m squared, which is this first term, and then bring down the negative 90. And now we have the four terms that I was talking about earlier. Okay, so we have a four-term polynomial, which means that we're now back in the territory of factoring by grouping. So if I look at these two terms and I factor out their GCF, they both have an m in common. Write that m on the outside, and then I'm going to factor that out or divide that out. I'm not going to show the division step yet, or because like we've already done this a couple of times, so I'm going to stop showing that step. So if I divide m out of here, I'm going to have an m left over. And if I divide m out of here, I'm going to have a negative 9 left over. Okay. So if I move over here, I can go ahead and factor out their GCF, which it looks to me like that's going to be a 10. So plus 10, open up some parentheses, and then I will say if I divide out a 10 here, I'll be left over with an m. If I divide this negative 90 by 10, I'll have a negative 9. And as I said in the last video, once these two terms or these two factors in the parentheses, if they're exactly the same, then that is now going to become our GCF. So I'm going to factor that out. M minus 9 is the GCF. We factored that out. And then what's left over is the factor m plus 10. Okay. So all of this stuff here, dealing with four terms, that was simply factoring by grouping. The only new sort of technique that we're employing over here is this scratch work that we're calling the AC method. Okay. But this m minus 9 times m plus 10, that's your factorization. Okay. So There are some things that you could do here to check yourself if you want to be um, very careful or very extra, I suppose, um, so that you don't get this wrong. You can always check yourself. And the way you're going to check yourself is simply by multiplying those factors out. So if I were to check to see if I got the right answer, should be able to take m minus 9 times m plus 10, and I should be able to multiply that out using the distributor property and have the same thing that I started with. So I should know that m times m is m squared, and m times 10 is positive 10m. Then negative 9 times m is negative 9m, and then negative 9 times 10 is negative 90. So at the end of this deal, I should have m squared plus 1m minus 90, which is the original trinomial. So that tells me that I factored this correctly. Okay. Do you have to check this every single time? Not necessarily. Once you start to build up the confidence, you can omit this last step. Okay. But it's going to take some practice, which is why we're going to do a few more of these to get used to that AC method part. Okay. So let's go. Let's take a look at number two. I have a trinomial, 1, 2, 3. And you might notice that there's a lot of sixes in this problem. Okay. So again, as a note, I want you guys to remember, always check for a GCF, a greatest common factor, because if we can factor out a GCF, then that's going to make the AC method a little bit easier for us. We're going to have smaller numbers to manage. So what do I mean by that? Well, if we were to just jump right into the AC method, we would have 6 times 60. And if you grab your calculator, 6 times 60 is 360. That's a very big number. That tells me that we're going to have a lot of factors of 360 that we're going to have to sift through to see if they can add or subtract to make this 66. We don't want to do that, okay? How can we make that number smaller? Well, if we factor out a GCF first, then we'll sort of reduce this polynomial in some sense. So if I have 6v squared, if I have a 66v, and I have a 60, I know that 6 divides each of those terms. So I'm going to factor out a 6. And if I divide 6 out of each of those, now I should have a v squared, a plus 11v, and then a plus 10. Okay? So now, as far as employing the AC method, I don't have to worry about this GCF that I factored out. I'm just going to say, well, what are my coefficients for this trinomial? V squared plus 11v plus 10. And we're going to label them A, B, and C. So if you need to do that over here, you can. I'm going to draw a little line here for my scratch work. A is equal to, what's the coefficient here? Should be 1. B is 11. And then C is 10. And it's called the AC method because we need to take A times C, which is 1 times 10, and we get 10. That's a much smaller number than 360, so we're just going to make our factor t-chart. 1 times 10, 2 times 5, 3 doesn't work, 4 doesn't work, and we're done. Okay, so what we want to do is choose the factor pair, and we only have 2 to choose from here. That's going to multiply. We need that pair to multiply to make positive 10, and they need to add or subtract to give us B, which in this case is 11. Okay. So we might notice that this number here is a positive. And it might not seem very straightforward, but there are two ways to multiply factors to get a positive. Either we have a positive times a positive, or we have a negative times a negative. Okay. So whatever factor pair we choose, we have to make sure are both of them positive or are both of them negative to meet these two conditions. Okay. So we might look at this second condition here, something plus something equals 11. And it might be super obvious in this problem. We need to choose 1 and 10 because 1 plus 10 makes 11. Okay. And, but I just said that we need to choose whether or not these are both positive or both negative. So if I choose for them to both be positive, well, 1 plus 10, that's going to give you positive 11, and that's going to be great. Okay. If you incorrectly chose that both of them need to be negative, well, negative 1 plus negative 10, that would be negative 11. So uh, we know right away that they should not be negative in this case. Okay. So if positive 1 and positive 10 add to make 11, well, we can rest assured then 1 times 10 also makes 10. So both conditions are met, which means we'll go back over to our three-term polynomial. Again, we're sort of ignoring the 6 for now. And we're going to take this middle term, the 11v, and we're going to break it up into positive 1m, I'm sorry, positive 1v and 10v. So I'm going to put 1v here, and that's a positive because we chose for them both to be positive, and positive 10v. Again, if I look at these two terms, the reason why we're using these factors, 1v and 10v, is because if we were to combine like terms, they give you the 11v. So we're not changing the value, we're just splitting up these terms so that when I bring down the v squared and the plus 10, that now we have 1, 2, 3, 4 terms for a polynomial, and we can begin factoring by grouping. Okay, so we'll take these two terms and say, what is their GCF? Looks like they both have a v in common. Open up some parentheses, and if I factor out that v, I should have a v plus 1 left over. Then if I look at these two terms, they both have a 10 in common, so I'm going to divide out that 10, open up some parentheses. If I divide out that 10, I should have a v plus 1 in common. Notice that the stuff in parentheses is exactly the same. Again, if it's not the same, then I've made a mistake. I made a mistake somewhere. It could be factoring out the GCF. Maybe I didn't choose the correct GCF, or maybe I made a mistake somewhere else doing the AC method. Maybe I chose the wrong factors. Okay. All of this stuff should be lining up. So if you do not have the same factors or the same polynomial in these parentheses on both sides, that means you made a mistake. You're going to want to start over. Okay. So here we go. We have these two, they match. So that tells us that our first factor is v plus 1. And our second factor is the stuff on the outside, the v plus the 10. And that's it. We have factored that trinomial. Um, Making one critical error here, and that is, what about this GCF that we factored out at the very beginning? Okay, that needs to be a part of your answer because when we write this in factored form, we need to write every factor that we have. So we have these two binomial factors, but you have to multiply that by 6 or put a 6 in front because otherwise that will not multiply out to give you the original polynomial expression that we started with. You would not get that 6v squared plus 66v plus 60. We need 1, 2, 3 factors for this problem. Okay. But once we do that, we should be good. Okay. Another one, we'll do it maybe a little bit faster this time. Okay. So again, first thing that we always want to start off by doing is check for that GCF. So do I have a GCF between 9k squared, 66, and 21? Take a moment to think about that. I'm thinking that it's going to be 3. Okay. Because 3 divides into 9. Surely it divides into 66, but it definitely divides into 21. So I'm going to divide out a 3. So I'm going to pull that 3 out of my original polynomial here. And I might grab my calculator at this point if I'm feeling a little bit fatigued. I might do 9 divided by 3. And I know I should have a 3k squared here. I should do 66 divided by 3. And I know that this should now be a 22k. And then 21 divided by 3 is 7. Okay, so that's now a 7. Now I can start with the AC method because certainly 9 times 21 would have been a much bigger number than 3 times 7. So we'll go ahead and draw our little line to keep our scratch work separated from the actual work we're doing with this polynomial. A is equal to 3, B is equal to 22, and C is equal to 7. Okay, then we're going to multiply A times C. So A times C is equal to 3 times 27, which is 21. And 21 doesn't have that many factors. It's 1 times 21, 3 times 7. 4 doesn't work, 5 doesn't work, 6 doesn't work, and then we're back at 7. Okay, so we want to choose the factor pair that will multiply to give us 21, but we need to choose the factor pair that will add to give us B, which in this case is 22. And if we look right away, this one's kind of an obvious case. 1 plus 21, I think is going to do it for us. So if we have 1 plus 21, that gives us the positive 22 that we need. And 1 times 21, that gives us the 21 that we need. So we need to meet both those conditions. So we always check that. And then we can move on from there. We'll go with this middle term here, which is a 22, and break that up into 2 terms. What are the terms that we're going to break this up into? Well, that's where these factors, 1 and 21, come from. Because we're going to say we have plus 1k and positive or plus 21k. Those two numbers, 1 and 21, they add to give us the 22, so we know that we've made the correct choice there. We'll bring down the positive 7 and the 3k squared, and then we'll hold off on this initial factor, that GCF that we took out at the very beginning, and just remember that it's going to be part of our final answer. But for now, we're just going to go ahead and proceed with factoring by grouping. So these two guys, looks like they have a k in common. I'm going to put k out, open some parentheses, and if I factor out a k here, I should have 3k left over. If I factor out a k from here, I should just have 1. These guys, 21 and 7, well, what divides into both of them? That's going to be a 7. So if I factor out a 7, I should have a 3k, and then 7 divided by 7 is 1. So we ended up with the same stuff in these parentheses. That means we're on track to finish this up. So this is going to be 3k plus 1 because we're factoring out the stuff in parentheses. And then what's left over, the k plus 7, that's your remaining factor. Okay. We can't forget that we factor out this 3 at the very beginning. We need to put that back into our answer. So once we do that, we're done. This is factored. Okay. All right. Well, you're going to need some practice with that, and definitely there's going to be some practice in the homework. But we need to move on to the last factoring technique, which is a little bit simpler than the AC method. Okay. In that you're going to have far fewer terms to deal with here. So let's take a look at something called the difference of squares. Okay. And we need a little bit of context here. Okay. Difference of squares refers to two numbers that on the face of it, they might not look like they are a number squared, but we have something that can be written as something squared minus another thing that is squared. What do I mean by squared? Well, mathematicians label special kinds of numbers perfect squares, and that refers to any number whose square root results in a whole number. So let's think about some numbers that you can easily take the square root of. Okay, and maybe I'll start in the middle of this sort of list of examples here. Let's start with 25. You guys should know that the square root of 25 is equal to 5, right? And if you don't know that, you can always grab your calculator and say, well, let's go ahead and clear that. What if I took the square root of 25? Do I get a whole number? Yeah, I get 5. All of these numbers, 1, 4, 9, 16, 25, 36, 49, 64, and so on, are called perfect squares because if you take their square roots, you get a whole number. So, for instance, the square root of 1 is a whole number. It's 1. So we could say the square root of 1 is equal to 1. So 1 is a perfect square. We can also say the square root of 4 is 2, right? And we can check in our calculator if we're being a little bit skeptical there. It's 2, a whole number, right? So its square root is a whole number. Many of you guys have memorized some of these perfect squares, okay? So you might know that the square root of 9 is equal to 3, that the square root of 16 is equal to 4, square root of 36 is equal to 6, the square root of 49 is equal to 7, the square root of 64 is equal to 8. Okay, and there might be a handful of other perfect squares that you've memorized, like the square root of 81 is 9, the square root of 100 is 10, okay? So there are some standard numbers that we should be able to recognize because they have nice, pretty square roots that are whole numbers, okay? So we're going to see a set of problems called factoring a difference of squares or using this difference of squares formula to factor, where we have something squared, a squared, minus something else squared, b squared. And whenever we have this scenario where the first number is a square or a perfect square, and the second number is a perfect square, then as long as there is a subtraction symbol between them, then we can use this formula to factor this binomial expression. So the reason why this is called the difference of squares is because in mathematics, subtraction is called a difference. Okay, so if we have the subtraction of two squares, one from the other, that's a difference of squares. Okay, so whenever we have this scenario, we're going to set up two sets of parentheses. And notice that on this side of the formula, we had a squared. If we took the square root of a squared, that should just turn into a. Okay? And if we took the square root of b squared, that should just turn into b. Okay? So when we're factoring, it's kind of like we're taking the square root of a, squared rather. We're taking the square root of this, and then we're just getting a. It no longer has that power of 2, and we're putting that here and here. Okay? They go in their own set of parentheses. Then we took this term, or yeah, this term here. We're doing the same thing. We're square rooting it such that we now have b here and here. Okay. Another way that you can think about it is that if I were to sort of reverse this formula, a times a is a squared, and b times b is b squared. The truth of the matter is that if you were to take this whole formula and distribute it completely, a times a times negative b times a, b times negative b, you would end up with something that looked like this, a difference of squares. That's why we can use this formula, okay? So let's see how this is going to play out in practice with some examples. So first, notice that we have two terms, okay? So when you have a binomial, which is two terms in that polynomial, you also need to make sure that this is a difference of perfect squares. So we're going to inspect this term here and make sure that whatever number or coefficient is attached to that variable, that it is a perfect square, and we also want to make sure that that variable is a perfect square. Okay, so based on the list of numbers that we looked at before, we know that 9 is a perfect square because if you take its square root, you get a whole number 3. Okay, and x squared is a perfect square because it's obvious we have that exponent of 2, which means that that is x squared. Okay. If we look at the next term in our binomial, that's a 1, which again, on the previous page that we looked at, we said that 1 is also a perfect square. So both 9 and 1 are perfect squares. Then we make sure that we have a subtraction symbol between them to ensure that we're dealing with a difference of squares. Okay, so as long as we have a squared minus b squared, we can sort of take the square root in some sense of the first term, and we'll put that right here. Okay. Then we'll take the square root of the second term. We'll put that right here. And as the formula states, we should have a plus sign here. And then our second factor is just going to be those same two terms, A and B, but this time we're going to subtract them. Okay, so one's a positive or one's an addition, and the other one's a subtraction. Okay, so what's the square root of 9x squared? Well, that's going to be 3x because 3x times 3x should be 9x squared. Okay. What's the square root of 1? Well, that's just 1. So this is going to play the role of A, and this is going to play the role of B. So once we figure that out, I can enclose them in parentheses. This first factor is going to be 3x plus 1, and the second factor is going to be 3x minus 1. So we still use A and B, but we have A plus B and then A minus B so that we're keeping in line with this formula. And that's it. That's how you use the formula. You are done. Easy enough. If you want, you can double check this by distributing everything out, and you should end up with what you started with, which is 9x squared minus 1. But I'll leave that as something that you guys can do on your own. Okay, so let's look at the next one. We want to employ this a squared minus b squared formula, which should factor into a plus b and a minus b. Okay, so again, it's like we're taking the square root of these to figure out what is a and what is b. So if I take the square root of this, well, actually, I'm getting ahead of myself. We definitely want to check to make sure, is this a perfect square? Well, 36, the square root of that is 6, so that is a perfect square. Okay, and then we have a squared. 25, is that a perfect square? It sure is. Okay, so now we can take the square root of this whole term. 36a squared should sort of reduce to 6a because 6a times 6a should be 36a squared. If I take the square root of 25b squared, that's going to be 5b because 5b times 5b is 25b squared. Okay, so I can close that up in parentheses, put a plus sign here, and then sort of copy 6a and 5b, and then this one gets a minus sign, and we're done with that factorization. So this is going to be your answer. Okay. All right. Now, those examples were just to get you used to this formula, but some of these problems don't immediately look like difference of squares. So you'll have to sort of process them and maybe use one of your other factoring methods before you can use the difference of squares formula. What do I mean by that? Well, if we take a look at 3n squared minus 75, and maybe we'll flip back to this table that we built of all of our perfect squares. Is 3 among this list of perfect squares? Well, I certainly don't see it. And even though I don't see 75 here, I kind of have a suspicion that that's not going to be a perfect square either. So what you might do to double check yourself is take the square root of 3. If we get a whole number, well, sure, that's a perfect square. But when you do that, you get this god-awful decimal number. That's not going to fly because we needed a whole number to call 3 a perfect square. So 3 is definitely not a perfect square. If we take the square root of 75, that's also not a perfect square. Okay. So what are we going to do here? You cannot forget your other factoring methods. Okay. At this point, we know how to factor out the GCF. We know factoring by grouping. We now know factoring trinomials using the AC method. And on the face of it, it doesn't look like we can use our difference of squares formula here. But those are the 4 techniques that we have at our disposal. What you should always do before you jump into any of these factoring methods, factoring by grouping, AC method, or the difference of squares, is you always should check to see if you can factor out a GCF, because if you can, well, then that kind of changes the game a little bit. Okay. So if I look at these two terms, I might ask myself, what is a number or a factor that divides each of these terms evenly, 3 and 75? And it turns out that both of these are divisible by 3. Okay, so if I divide this by 3, I should end up with n squared. And if I divide 75 by 3, 75 divided by 3 is 25. Okay. So I was able to factor out a GCF at the very beginning. And now when I look at this polynomial in parentheses, I can ask myself, well, are these two terms perfect squares? And sure enough, they are. Okay. So you might say to yourself, well, what's the square root of n squared? Well, n times itself gives you n squared, so its square root must be just n. What's the square root of 25? Well, that's going to be 5. So if I'm employing this difference of squares formula that I've been using, then I need a plus here, and then I can copy this over and say n minus 5 has to be my other factor. We can't forget about this GCF that we took out, so I'm going to put that as part of my answer. And these 3 things are the factors for my original problem. So now we can say that we're done. Okay? So you've learned 4 different factoring techniques. And it's not the case that you're just going to use them in isolation. Sometimes you have to combine these factoring techniques. And as we've seen, we learned factoring out the GCF so that we could build that up to factoring by grouping, which is really just factoring out the GCF 3 times. Then we learned the AC method because that's just a technique that helps us take a 3-term polynomial back to a 4-term polynomial so that we can factor by grouping yet again. And now we have our special difference of squares formula, and that's going to round out this discussion of factoring. But I can't emphasize this enough. Factoring is going to form the foundation for everything we do for the rest of the semester, okay? If it seems complicated and it feels like you can't get it, you need to practice more, because you're going to see that we're going to run into solving different kinds of equations like quadratic equations, polynomial equations, rational equations that all will involve at some point factoring, okay? So it's not something that we can run away from. Make sure that you're studying this and asking questions whenever you get stumped. Make sure that you're sending me messages with your queries and your questions, and that you're going to tutoring to get that assistance. There's no time to delay, so make sure you're getting that assistance. And whenever you have to watch these videos, I know that I can be a little bit long-winded and boring. If you need to turn up the speed or skip through them, totally understand. I'm not going to be offended. Just make sure that you're doing what you need to do, and I'll see you guys on the next video.